Welcome to BIOE 3310 Fluids. And today we're going to split the lecture into two parts. So part one is going to be talking about flow between parallel plates. So imagine I have two parallel plates, for example, these two cutting boards that I have here. Let's just put one of them down right here. And then let's say I take some viscous fluid, honey, and squirt it all out over this plate. I don't want to make a mess, so I'm not going to actually do it, but imagine I squirted out a whole ton of honey on this plate, and then I sandwiched that honey between these two plates. And then so you can see how there's like a gap between these two plates, and the honey sort of fills the gap. Then let's say I took this top plate and applied some force to it and wanted to drag that plate across. So I'm not moving the two plates closer or farther apart, but I'm just dragging it across. And you can imagine all of the honey that I squirted in that plate experiences some shear stress and needs to get sort of stretched and deformed as the top plate drags across the bottom plate. So that's the system that we're dealing with. So we're basically framing this lecture around flow between parallel plates. So I don't think too many of you are going to make a career out of flow between honey and cutting boards. So I'm going to sort of preface this with a discussion of why we care about a flow like this. Then we're going to sort of solve an example problem which makes use of this flow. And so why we care, we're going to talk about applications, particularly in BIOE. Then we're going to use this as an opportunity to really solve an example problem, to use the mathematical and physical tools that will help us solve problems in fluid mechanics. So we're going to talk about things like a velocity gradient, and versus a velocity profile. What's the difference between the two? What is this language that we're using to help us describe flows in fluid mechanics? Then we're going to sort of frame this problem in a mathematical, calculus, algebra sort of way, and this is going to help us. And the steps we're going to talk about shear stress. We're going to end up setting up a differential equation. And then we're going to solve that differential equation. So we're going to integrate, and we're going to apply boundary conditions. And again, if some of these terms are unfamiliar, it's okay, right? This is an opportunity to learn. So we're going to sort of be this is an opportunity for sort of to teach you, how we can solve differential equations in fluid mechanics, and where integration in the calculus sense is going to come in, and what are boundary conditions, and how do they help us solve a differential equation. And then finally, we're going to make a connection between shear stress and the forces to generate it. So to generate that shear stress. So what's the connection between force and shear stress? So we sort of talked about it a little bit last time, but now we're sort of going to back it up with a little bit of algebra. Basically, how much the problem we're ultimately shooting for is, if I want to move this yellow plate with some velocity, how much force am I going to need to apply to do that? And of course, force relates to shear stress. Shear stress relates to the velocity gradient, as we talked about last time for Newtonian fluids. So we can make a connection between how much force I need to apply to this plate and what velocity that plate is going to be moving at, and of course some other parameters in the problem as well. So that's where we're going. So this is going to sort of serve as an outline and topics for what we're going to cover in the rest of this lecture. So I know it's a little contrived, right? Honey between cutting boards, and obviously this is a very rough example that I'm giving to sort of illustrate the essence of this problem. But we might encounter problems like this in bioengineering. We might encounter not exactly honey between cutting boards, but we might encounter similar flows with similar phenomena. So for example, examples where we might encounter such a flows is in our joints. So there's cartilage. Right, so let's say I have a knee. The top part of my knee maybe stands still if the bottom part of my knee is moving, or even in my fingers, right? I have one joint where one part of the joint stays still, the other part of the joint moves, and there needs to be some interface between those two joints. So there's one chunk of cartilage at the top, one chunk of cartilage at the bottom, and there's typically what's called synovial fluid. There's typically what's called synovial fluid between the two pieces of cartilage, and that synovial fluid is kind of the same as the honey in this example. So we might be concerned with how much shear stress arises when I'm moving my joints in various ways, based on things like the viscosity of the synovial fluid and the geometry of the joint. Right? And this is particularly important in bioengineering if we're trying to maybe analyze damaged joints for cases like arthritis. I might also care about flows like this if I'm trying to squeegee something. So maybe I have some surface and there's some fluid on that surface, and I want to drag a squeegee across that surface to, let's say, try to clean off the fluid or move things around or something like that. I might be interested, hey, is this squeegee going to damage the cells underneath, or damage the surface? Is there stuff in the fluid, something like that, right? So one example is we used a squeegee-like technique to try to lift cells that were growing off of the surface of a cell culture flask. So we had some cells growing on that surface, and we wanted to know, hey, if I drag a squeegee across that surface, is that applying enough shear stress to try to dislodge the cells, but not so much shear stress that it damages the cells? So we were interested in flows like this to try to get a connection between velocities and forces and shear stresses and biological applications. You encounter flows like this in the body. For example, if you have an eye and you put a contact lens over that eye, and then you have your eyelid that closes over it, well, as your eye opens and shuts, it drags across the surface of the contact lens or the surface of your eye if you don't wear contacts. And you have tears over your eyes, and that tear, sort of serves as a role of a lubricant between the eyelid and the eye surface. So, so we might care about, hey, is the closing and opening of our eyes putting so much shear stress on our eyes that it damages the cells underneath? So for example, if you don't have tears, then you can have much more shear stress between those things than you would if you did have tears. And we'll make connections between the geometry of this flow and shear stress later on, once we kind of get to our mathematical results. And then a final thing we might be concerned about, maybe less in the bioengineering and more in the sort of general engineering sense, is safety for slipping. So for example, if you have a floor and you have someone's foot on that floor and you have some wetness underneath the foot, how does the sort of thickness, if the foot is trying to move across this surface, does that provide so little shear stress that the person ends up slipping and moving much faster than they expected to? Right? So whether it's feet on slippery floors or tires on slippery roads, we care about the flow between one plate that's moving and another plate that's not moving, a fluid in between them, and the connection between velocities, geometries, fluid viscosities, and shear stress. So you can take a minute now and pause and ponder any other examples that you might think of You can leave them in the comments, either on Canvas or on YouTube. If you say, hey, are there any other examples where you could have this flow between two parallel plates where one's moving and one's stationary, and there's some viscous fluid in between them, and you might be interested in predicting things like forces and shear stresses and velocities and the relationship between all of those. So pause and ponder if you care to. All right, so thus concludes our discussion of why we care about flow between parallel plates, particularly in the context of bioengineering. Now, let's start kind of getting into the mathematical meat of this problem by talking about things like a velocity gradient and a velocity profile. What are these two things? How do they relate to one another? How are they different from one another? So, let's do a quick recap of the velocity gradient, which is essentially describes the variation of velocity with space. Right, so if we anticipate solving this problem where we have, let's say, the ground that's stationary and a plate on top of it that's, let's say, moving with some velocity, of the plate, we anticipate spatial variation in all of the fluid that's between them, right? So maybe I'll define a little coordinate system, let's say x and y, like this. I would anticipate that velocity of the fluid is going to vary with y, right? So velocity of the fluid will vary with y, right? Because the fluid molecules that are very, very close to the bottom plate here, they're essentially not going to be moving at all because the plate right next to them is kind of holding them back from moving. Whereas if we consider the molecules of fluid right next to the plate, right next to the top plate, those molecules are going to be dragged along at essentially whatever velocity the plate is. And any molecules in between are going to be somewhere in between this zero velocity at the fluid at the bottom and the velocity of the plate at the top, right? So we anticipate velocity of the fluid varying with y. And this is, of course, in contrast to things like mechanics, right? In things like mechanics, right? In mechanics, we talked about velocity as if it was some kind of singular quantity, right? Like there was a single ball with a single velocity that kind of described entirely what that ball was doing, right? So velocity was this kind of like one essential thing. It was a single number for a single object. We contrast this with fluid mechanics, and in fluid mechanics, because velocity will vary with y, we anticipate that velocity is a function. We need to describe velocity as a function of space, right? But molecules here have different velocities from molecules here, so velocity is often a function of space x, y, z, and time t. Right? So we have flows in general where all of the points of all of the particles of all of the fluid, any of those particles could have different velocities from any of the other particles in the fluid. So velocity could vary depending on where we are in the fluid and also at what time we're analyzing all of those velocities. And this is in contrast to mechanics, where usually we describe velocity just as a function of time. Something like that, right? We didn't really describe spatial variations in velocity. But for fluids, we need to keep track. We need a function to describe the velocities of all of those different particles, all of those different fluid particles. So velocity gradient is important in this that velocity varies spatially. So a velocity profile is essentially a velocity as a function of x, y, z, and time. And a velocity gradient is a derivative of this velocity with respect to space, right? So for example, a velocity gradient, and there can be multiple velocity gradients. There can be a velocity gradient with respect to y, or x, or z, or t. In this case, we'll have a y velocity gradient, right? So a velocity profile is the velocity of the fluid as a function of all of these variables. The velocity gradient is the derivative of that velocity with respect to a spatial variable. So it's the derivative of this velocity function with respect to a spatial variable, i.e. an x, y, or z. So that's basically the difference between a velocity gradient and a velocity profile. Velocity profile is the function, and a velocity gradient is a derivative of that function with respect to x, y, or z. So now that we've talked a little bit about velocity gradient, a little bit about velocity profile, and how we anticipate there being a velocity profile between these two plates and a velocity gradient, let's talk about how this, why we might care about a velocity profile, why we might care about a velocity gradient, how that relates to shear stress and all this stuff. And why we might want to try to investigate or solve or figure out a function for this velocity profile. So let's frame our problem a little bit more quantitatively. All right, so imagine I have a plate, a top plate, and let's say the ground underneath it. And let's say I'm moving this plate with some velocity, and let's say it's a known velocity, v plate. Let's define a coordinate system that's kind of centered on the gap between the plate. So let's put x in this direction, and we'll put y that kind of starts at the bottom of the plate and points upward, like here. Z is kind of this direction going into the page, but we're not going to care too much about z for now. Right, so let's say if I had some velocity of the plate and had some thickness of the gap, let's call it h, between the floor, or between the non-moving plate, the ground, and the moving plate. Let's say there was some known thickness h between those, and let's say there was some fluid in the gap, and the fluid had a viscosity, some known viscosity, let's call it eta. So if the fluid had some known viscosity eta, the plate had some known velocity v plate, and there was a gap between the top plate and the bottom plate that had some known thickness h. Our goal is to basically say, hey, if all of these are knowns, what force would be required to sort of sustain the motion of this plate in steady state? I.e., if I were to maintain this plate at its constant velocity v plate, how much force would I need to keep applying to that plate in order to keep it there? Right. So just as a sort of color coding scheme, for most of the problems I solve in most of the notes in this class, I'm going to try to keep any sort of known constants in blue, and any unknown variables that we're trying to solve for, I'm going to put in red, right? So I'm going to basically say, hey, if we're applying some force, we have some unknown force, some force applied that we're trying to solve for, that is supposed to keep this plate in motion in steady state. So this is what we're trying to solve for. Oh, one last thing that we'll need to know is what is the sort of area? What is the area of the plate? Sorry, forgot to tell that. That's going to be an important variable that we know. Right, so all the stuff in blue we're going to treat as knowns, and where we're looking to solve for what this unknown force would be. And one step along the way is we know that forces, if we have this idea of forces in areas, we're probably going to need to work through shear stress. So the idea is we're going to make some connection between force and shear stress. If we remember, there's a connection. If we have some Newtonian, if we have some fluid with some viscosity, there's going to be a connection between shear stress and, if you dust off your notes from last time, velocity gradient. We just talked about earlier that there's a connection between a velocity gradient and a velocity profile. So if we have some connection between velocity gradient, we're going to need a connection between velocity gradient and velocity profile. And so we're going to need to basically figure out what the velocity profile is between these two things. Well, and we might get information about this velocity profile from what the velocity of the plate is and what the velocity of the ground is, right? So we might have a connection between what the velocity profile is and what our boundary conditions of our system is. So we might be able to get a connection between the velocity profile, which is of the fluid, and the velocity of the plate, which essentially describes sort of what's happening at the boundary of the fluid. So we can kind of get at all of this information. We'll sort of look at this chain, these connections between all of these things, and that's going to sort of help us solve for what this unknown force is, given these knowns about our system. All right, so let's take a side view. We have the plate on top, the ground underneath, X and Y. And our goal is to kind of work out sort of all of this stuff, right? So, if we can get the velocity profile, that can help us with all of this stuff here. So, a lot of times when we're solving this problem, and again, we'll do a lot of practices with this, and we'll work it out a little bit more rigorously later. But sometimes we like to imagine just a little chunk of fluid kind of in the middle, and so oftentimes analyzing a little chunk of fluid will help us sort of derive an expression for what the whole velocity gradient is. So oftentimes if we analyze just a little chunk of the fluid, then we'll get information about the whole velocity gradient, and then once we have information about the whole velocity profile, then we can get sort of all of the information we need about the problem. So let's analyze one little chunk of fluid. Now we can imagine, let's say this point of the fluid, let's say that's at point Y, and if we might imagine a point on the top of this little chunk of fluid, this point at the top would be at a height y plus delta y if they're separated by a distance delta y. And you can imagine if I'm moving this plate over here with some velocity, I'm trying to drag the top of the fluid this way, I'm trying to drag the bottom of the fluid this way, right? So if I'm thinking about it, if I'm moving this plate in such a way, like there's gonna be shear stress. There's gonna be shear stress in here. Right? So there would be shear stress in these waters. And if we go back to the previous lecture's notes, let's just imagine that there's some shear stress on this chunk of fluid. right? So, and if we think about shear stress, we might, we'll need to oftentimes, it's a little tricky to try to intuit what directions all the shear stresses and all that stuff is going to be. So in these cases where we can't rely exactly on all of our intuitions for some of these things, especially with weird conventions for shear stress and stuff like that, let's just define shear stress in the directions as indicated, right, by the convention. And if you remember, if you look back at the convention for positive shear stress points to the left on the top and to the right on the bottom. We're using the convention in the book and that some chemists, chemical engineers and fluid mechanicians use. So we can imagine there's some the shear stress on the bottom is tau, and it's tau associated with forces in the with a normal that would be in the y direction, and with forces in the x direction. So this is tau yx, and it's at location y. So it's tau location at y. And up here, we have some tau yx, right? Because it's still associated with a normal in the y direction and forces in the x direction. But this is tau yx at y plus delta y, right? So we have some shear stress on the bottom, some shear stress on the top, and hypothetically, these two shear stresses could be different from one another. So let's analyze this a little bit further. So let's go through with some reasoning to see if we can get some more information about these shear stresses on the top and on the bottom of this chunk of fluid. So we'll proceed with an analysis almost the same as what you would do if you were doing a free body diagram back in mechanics. So we have a little chunk of fluid. We have some forces associated with shear stress. So, there's some shear stress, some shear stress pointing this way on the top. And we're calling this tau yx at y plus delta y. And we're calling this shear stress tau yx at y. And let's sort of think about some other forces that might be present on this. Well, we know that a lot of times gravity pulls things down. So we could basically say there's some gravitational force pulling down on this chunk of fluid. But also we know that the rest of the fluid underneath this chunk of fluid is supporting it in the other way. So, there's probably some what actually is pressure, but we'll just sort of imagine it as like a normal force pushing it back up. We're going to assume there's sort of no pressure gradients in the x direction. And pressure gradients is a term we're going to talk about later, but we're basically assuming that there's not any sort of pressure pushing on this side or pushing on this side, that we're just moving the plates. We're not trying to blow the fluid through the plate. We don't have some sort of pump trying to push the fluid. So we're assuming no effect of pressure in the x direction. So if we're sort of looking at all of these forces, we might be able to kind of get some more information about shear stress here. So what we know is that if you sum the forces, and in particular if you sum x forces, then that's equal to mass times acceleration. If we're sort of considering this chunk of fluid as like a body, like you would in mechanics, but take a moment and pause and ponder. What is this right-hand side? What is the right-hand side of this equation? So what is the right-hand side of this equation? And with that, and when you're thinking about that, think about some of the assumptions that we made in this equation, or in the development of this problem. So pose and ponder. What's the right-hand side of this equation? So hopefully you paused and pondered. And the key thing here is we have information about what's going on. So in steady state, if we consider a steady state, the top plate is moving at some constant velocity, and all the fluid in this is also going to be moving at constant velocity. So if velocity if velocities are constant with time in this system, then this little chunk of fluid, if we sort of treat it like an object, treat it like a mass, if it's just trucking along at constant velocity, then there's no acceleration. There shouldn't be any accelerations. So what does this mean? If we sum forces on this little chunk of fluid, then it should be equal to 0. So this equals 0. Well, if we think about it, the only forces in X are these shear stresses, right? We have some Y forces from gravity, some Y forces from a normal force. But if we sort of assumed that pressure wasn't pushing this chunk of fluid, and again, we'll talk more about pressure later in this class. But if we think about this, the only X forces are really the ones associated with this shear stress. And if we need to sum forces such that they balance out, the shear stress on the top of this chunk of fluid has to be the same as the bottom, because they basically need to cancel out in order for the sum of forces to be 0. So these need to be the same. So what does that mean? This basically means if the shear stress on the top of some chunk of fluid is the same as it on the bottom, and this chunk of fluid here could sort of be the same, we could analyze this the same for any chunk of fluid in this entire system. What does that mean? If the shear stress on the top and bottom has to be the same, this basically means that shear stress must be a constant. So that means shear stress must be a constant in this system. So let's now proceed with what the implications of this shear stress being a constant. So we've concluded that shear stress is a constant, but the tricky thing is we don't necessarily know what it is, right? So it's a constant, but it's an unknown. It's an as of yet unknown. It's an as of yet unknown constant. But even though this is an as of yet unknown constant, we might be able to work some stuff out, right? So ultimately, we're trying to work out a relationship between our applied force and some other knowns, some other known parameters in this problem. And force is related to shear stress. Shear stress is related to, wait a second, shear stress is related to velocity gradients, right? So we've just worked out some information about shear stress in this problem. So if we can relate shear stress to velocity gradients to velocity profiles, and velocity profile to some known quantities, we'll then be able to work all the information we need to deal with force. So let's try to work out this relationship between shear stress and velocity gradient. So if you look back in the notes, if we assume this fluid is Newtonian, there's a relationship between shear stress and a velocity gradient that we can use. So let's put that down. So shear stress is equal to minus eta, which is the viscosity, times the velocity gradient. Times dvx dy. Right, so and this relationship is what came out of this is our constitutive relationship that we worked out, right? So assume fluid is Newtonian. Here we have our constitutive relationship. So shear stress is something that's as of yet unknown, but we're starting to get it in relationship. We're starting to get a relationship between this unknown shear stress and some quantities that are known. So just a quick reminder for this problem, red is going to be things that are unknown, and blue are going to be known constants. Known constants or given constants. And black is going to be stuff that we haven't quite worked out yet. So black is things that are to be determined, haven't quite worked out yet. For example, what this velocity profile is. So here we have it. Shear stress is a constant, but it's an as of yet unknown constant. But we have this constitutive relationship to help us out. So I'm just going to I'm going to skip a few steps here, and we'll talk about these steps that I'm skipping in a little bit more detail later in this class. But strictly speaking, these are partial derivatives here, and we can replace any partial derivatives with ordinal derivatives if we assume Vx is a function of y only. So if our x velocity is a function of y only, then we can replace partial derivatives with ordinary derivatives. And this is kind of reasonable, basically. You know, we don't expect x velocities to vary too much in this part of the plate versus this part of the plate, right? All those fluid particles are going to be moving along in the same direction. But we do anticipate a lot of variation of the velocity in y, right? So, you know, the particles down here won't be moving at all. The particles close to the plate will be moving very fast. But, you know, the particles right here have got to be moving the same speed as the particles over here, right? So velocity is not going to be a function of x, but it is going to be a function of y. So we expect x velocity to be a function of y only. And if that's the case, again, we'll talk about the mathematics here a little bit more rigorously later in this class. But we can basically replace the partial derivatives here with ordinary derivatives. Hey, wait a second. What do we have here? Let's pull back to our outline. So we have flow between parallel plates. We talked a little bit about shear stress, and we know we're going to work towards a differential equation, which we just got here. Hey, wait a second. What's this right here? This is a differential equation. Can we try to solve this differential equation? So can we solve this differential equation? Well, yeah, actually. I mean, it's a little bit tricky, but I mean, as far as differential equations go, it's not too bad, right? So here we have a couple of constants and one derivative. So this isn't as far as differential equations go, not too bad. So let's work it out together. So we have this differential equation here. If we want to solve this differential equation, we can solve it via integration. So let's just sort of reformulate things a little bit. So we'll have dvx dy, and we'll just sort of bring all the constants to one side and bring the derivatives to the other. So we have this. So we have this is our differential equation, and we can solve this via separation of variables, right? So we can bring our dy over to one side of the equation, so we can have an integral dvx is equal to minus tau yx over eta dy, and I guess we'd be integrating both sides, right? So dy. Can we solve this differential equation? So take a moment now, pause and ponder. Can you integrate? Can we solve these integrals? So hopefully you've paused and pondered. Now, if you integrate just d something, then you get that thing, right? If we integrated dx, we would get x. If we integrated dy, we would get y. So if we just integrate dvx, then the left-hand side becomes vx, right? If you integrate d something, you know, it's sort of like integrating 1 times dvx, right? So if we integrate 1, then we get whatever that thing that we were integrating with respect to. So that's our left-hand side. If we notice, hey, wait a second, all of this stuff right here, does any of this stuff depend on y, right? Tau yx, well, we already concluded this was a constant and this was a constant. So anytime you have constants inside of an integral, if we can pull them out because they're constant, right? If we have constants inside of an integral, we can pull it out. And then at that point, we just have an integral dy. So, well, if integral dy, then we get y as our integrand. And of course we need to keep track of these constants that we had as well. Hey, wait a second. Are we all done? So pause and ponder. Are we all done? Are we done with our integration? Well, perhaps those of you who have dusted off your calculus notes or remembered your high school calculus a little bit, when you have these indefinite integrals without limits of integration, when you have an indefinite integral and you integrate, you gotta have the plus c, right? Remember plus c from high school calculus? Yeah, that's going to be important in this case, right? And because this is a constant of integration that we haven't quite worked out yet, we're going to have to treat it as some unknown constant. So that's why I put it in red. So we've solved this differential equation by integrating. It actually wasn't that bad of an integral, right? It was just integrals of a constant. We did it. So now we have this. And if you notice, this is the workings of a velocity profile. Right? This is the workings of a velocity profile. What is a velocity profile? Well, if you remember back in our notes, right, this velocity profile is a velocity as a function of x, y, z, and t. Right? And we hope that we can get this velocity profile to help us solve parts of this problem, right? Because we know if we have a velocity profile, we might be able to make a connection between that function of velocity and information that we have about velocity at the boundaries. So the velocity of the plate might help us deal with this velocity profile. We already made a connection between the velocity gradient and the velocity profile. We did this by integrating. So we're working towards being able to relate force through all of this stuff to information that we know. So this velocity profile that we got is a step towards creating connections between things that we do know and things that we have yet to figure out. So we have information about a velocity profile. We have the form of the velocity profile, but what might be a little bit tricky about this result that we got, we still have these unknown constants within our velocity profile. So how do we deal with unknown constants, for example, constants of integration or other unknowns within our system? So we deal with unknowns via boundary conditions. So we deal with unknowns via boundary conditions. And boundary conditions will often take the form of, what is velocity at some edge, at some known point in the flow? So what is what is x velocity at some known point? What is x velocity at some known point in the flow? Well, if we think about, the points that we have the most information in the flow, the points that we have the most information in the flow are the fluid particles that are right next to the plate and the fluid particles that are right at the bottom too. So let's think about what these boundary conditions are. So we'll put our boundary conditions right here, and we can basically say Vx at y equals 0. Well, what's Vx at y equals 0? Right, so we put our origin kind of at the bottom plate here. So what's our x velocity of the fluid right at y equals 0? Well, the bottom plate is not moving, so the particles immediately adjacent to that bottom plate also can't be moving. And this is what we call a no-slip boundary condition. Right, so these fluid particles right at the bottom plate, their x velocity has to be 0 because that the bottom, the ground is not moving. Right? But we have two unknowns here in our velocity profile, so we're actually going to need two boundary conditions to help deal with those unknowns. So we're going to need a second boundary condition, And the second boundary condition is what is our x velocity at y equals the top plate, right? So we put our origin here at the bottom, and so at y equals capital H, right, i.e. the gap height between the two plates, at y equals h, that x velocity must be, well, the plate, right? The fluid particles immediately next to the plate must be trucking along with that top plate at a velocity v plate. So how does that help us? How does that help us solve this problem? Well, we can essentially substitute in this into this equation and get one equation, and then we can substitute this into this equation and get another equation. And then we'll have a system of two equations and two unknowns. So let's do that. So let's make those substitutions. So let's substitute this equation in here. So Vx is 0, so we'll put 0 in for the left-hand side. And at y equals 0, we sub y equals 0 right in here. So the first term on the right-hand side is going to be 0, right? This whole thing becomes 0. And then we just have plus c. Ooh, getting some information here, right? So this equation comes from our first boundary condition. And then we have our second boundary condition. We'll sub in v plate for Vx. Equals, we'll sub in y equals h right here. And of course, we still need to keep these constant terms out front. Plus, and we have plus c. But right away, we look at this first equation and we know that c has to be equal to 0, right? And if c equals 0, then we can get rid of, we can then sub in the result from this first equation into this second one. So what does that mean? Well, we figured out that c equals 0, and then if we look at this last equation, that gives us all of the information we need to figure out the shear stress, right? So what does this mean? Tau yx has got to be equal to, we can bring eta over and h over. So we get v plate over h times eta and a minus sign. So what does this mean? We now have all of the information we need to work out a couple of things. One is we have all the information we need to figure out this velocity profile. And the second thing is we now have all of the information we need to figure out shear stress. Okay? So what did I promise? I promised that there would be there's a relationship between force and shear stress and velocity gradient and velocity profile and the velocity of the plate. And we've now worked out pretty much fully what that relationship is. We're on the home stretch. Woohoo! So what's this going to look like? So we have one important result. Here's this expression for shear stress. And then another important result is what we can get if we plug this back into our expression for the velocity profile. So let's do the velocity profile part first. We get Vx is equal to, and we can sub in this expression for shear stress back into our Vx equation. And if you do that, you end up with, here, so we have minus V plate over h times eta times 1 over eta times y plus 0, right? And I'm just neglecting. I'm already subbing in and not even bothering to include that plus c because we know it's 0. Hey, wait a second. We can make a couple of cancellations here. If we notice this eta cancels with this eta, and this minus sign cancels with that minus sign. So what do we have here? Vx is equal to v plate times y over h. So this is a cool result. So what does this result mean? Well, if we think about it, Vx is this function of y, and this is what we call the linear velocity profile. This is what we call the linear velocity profile. Why is it linear? Well, if we think about it, this equation sort of has the form like y equals mx plus b, or vx equals some constant times y plus a y-intercept, which is 0. Right? So what does this mean? If we wanted to plot, I'm going to sort of like rotate my axes a little bit. I'm going to put y here and vx here. We imagine the top plate right here, you know, the ground right here, and our x velocity is basically starts at 0 at y equals 0, and it linearly increases until it matches v plate. And this kind of makes sense to us too. Right? You know, if we have this top plate moving and the bottom plate standing still, fluid particles in between are going to, you know, be speeds that are in between v plate and 0, right? So we have this velocity profile, this linear velocity profile, where the top basically matches the plate, the bottom matches the bottom plate, which is 0, and things in between, you know, are sort of linearly, you know, are sort of proportionate, right? You know, a point halfway in between the two has half of the velocity of v plate. So this is what we call the linear velocity profile. So before we get too far, you know, trusting our results, it's always good to do a couple what I'll call sanity checks, a couple checks to make sure we didn't make any mistakes. So I'm going to copy the velocity profile result that we got here. So Vx is equal to V plate times y over h. So there are two checks that I like to do for almost all of these problems. So the first check is just to make sure that this indeed does satisfy our boundary conditions again. So if I plug in, so double check boundary conditions. So if I plug in y equals 0, then this whole equation becomes 0. And that's consistent with the 0 velocity that we have at y equals 0 down here. If I plug in y equals h, then I get h over h. So Vx is just V plate, and that's consistent with what I get up here at y equals h. So boundary conditions check out. Excellent. The second check is what I'll call is for the units. And this sort of brings back this idea of dimensional homogeneity, i.e. that the units on one side of the equation have to be the same as the units on the other. So throughout this course, I'll kind of use this example. So my very first semester that I was teaching here, I was developing the notes for one of my lectures, not for this course, but for another course, and I had made a mistake in my notes. It was also the very first semester that I had a newborn daughter. So I was up. It was 2 a.m. I was working through my lecture notes. My daughter was crying. I was crying, and I realized that I had a mistake in my notes because I checked the units, and the units on one side of the equation didn't match the units on the other. And eventually I worked back, I found my mistake, I corrected it, and the baby stopped crying right at that moment. So we'll say, baby you-know-who really likes it when the units match up, right? So for baby you-know-who's sake, let's check for dimensional homogeneity. So if we think about the left-hand side of the equation, this is going to be a velocity. So that's going to be meters per second. And we should check to make sure that it equals the units on the right-hand side. Velocity of the plate, that's also going to be meters per second. Y is going to have units of meters. H has units of meters. These cancel out, so we get meters per second for meters per second. All life is good. So this checks out. Great. So we've done two checks to make sure that our answer is sensible. And we have an expression for this so-called linear velocity profile. Now, let's work out our overall goal, which, if you recall, was to determine what force we need to apply to this plate in order to sustain the plate with some velocity, the plate. So let's work that out. So if we know the force that we're applying to this plate must essentially counteract the shear stress on the bottom of this plate, right? So if you imagine I have my plate like here, I'm applying some force to it here, but on the bottom of the plate, there's all that shear stress. There's all that shear stress, essentially holding me back, right? But the way it's defined, physically we know the shear stress is kind of dragging back on the plate here. But if you recall from our definition of shear stress, tau yx is sort of and the way we worked it out in this problem, and using our constitutive relationships, tau yx is sort of defined to have been pointing to the right in this case. So here, our tau yx is in a sense pointing like this, right? But we can't essentially equate forces in shear stresses. We need to translate this shear stress to the force that results from the shear stress first, right? So what is the force from shear stress due to this tau yx? Well, if we think about it, shear stress is force divided by area, right? So shear stress is force over area. So if we wanted to translate a shear stress, right? So shear stress is a force over an area. So what does this mean? So this means the force from a shear stress is basically going to be equal to tau yx times what area this shear stress is acting on. And this shear stress is acting on the area of this bottom plate, right? So the shear stress is acting on the area, the underside of the area of that plate. So in this case, but if we look back at our problem formulation, I said the area of the plate was one of our known constants, right? We assume we know how big that cutting board is that we squirted the honey on. Right? So in this case, the shear stress force is equal to tau yx times the area of the plate. So what does this mean? Well, if we know the plate is also in steady state, right? We said it's moving at some constant velocity, the plate, then the sum of forces in the x direction on the plate must be equal to 0 because it's not accelerating, right? The plate's not accelerating. So what does this mean? Well, we have our applied force in the positive x direction. And we also have this force due to shear stress acting in the x direction too, right? And I'll just kind of sub that right in as tau yx times area of the plate. So, hey, wait a second. But, here I wrote tau yx in red, but from our earlier analysis in this problem, we actually found an expression for tau yx in terms of entirely known quantities. So let's go ahead and sub that in. Let's go ahead and sub in this result. Right? So we can sub in this expression for tau yx into this right here. And when we do that, we'll have our applied force entirely in terms of knowns for this problem. So what result does this give us? Where the AP comes from this, and this was this expression for tau yx that we had earlier. So we can solve this equation for our applied force to get this following result. And there we have it. So, woohoo! We solved it. Let's go get some ice cream to celebrate. Now, but before we can go get ice cream to celebrate, let's do a couple of checks. And this time I'm actually going to do two checks that are one similar and one different from the one before. So one check that we can do. What's a sensible check that we can do? Well, to make sure baby you know who doesn't cry, we got to make sure the units on both sides match up, right? So our force applied, that's going to be in newtons, which is equal to a kilogram meter per second squared. And we want to see if this balances all the stuff on the right-hand side. So we have our velocity of our plate, which is meters per second, h, which is meters, viscosity, which if you dust off the notes, has units of kilograms per meter second, and the area of the plate, which is meters squared. So take a moment, pause and ponder. Are we okay? So hopefully you've paused and pondered at this point. Our meters squared cancel with those. The 1 over seconds in the numerator and the seconds in the denominator make it so we have seconds squared from each of these. And then we have a meter and a kilogram here. So we have meter and kilogram. From this. And hey, wait a second. Meter kilogram per second squared? Meter kilogram per second squared? Great. We're okay. One additional check that I like to do is the following. So another check is basically look at what happens to our applied force when various things go up or go down, right? What, does our applied force scale in sensible ways when I change things about my algebraic result that I got here? So let's go through each of these things and determine if they increase, what happens to our force applied, right? So if V plate goes up, what happens to our applied force? Well, if the velocity of the plate is bigger, then our applied force also increases. And this makes sense, right? If I'm trying to drag my top plate very quickly as opposed to just barely moving it at all, it makes sense that it's going to require more force to deform the liquid more quickly, right? It's, if you're swimming through the water or something like that, if you're trying to drag something through some viscous liquid, it requires a lot more force to make that stuff happen faster than slower. So as the velocity of our plate increases, our required applied force needs to increase proportionately. If the viscosity of our fluid goes up, what happens to our applied force? Well, if viscosity goes up, our applied force also has to go up. Our applied force also has to go up, right? And this makes sense. If I had my two plates here and I put honey in between them as compared to water, the water, or air even, air, there's going to be barely any resistance between moving these things. Whereas if I had honey, got to drag that honey, right? So the more viscous the fluid, the more force required to do it. An additional thing, what happens if the area of the plate goes up? The force also goes up, right? So in this case, when the area of the plate goes up, the applied force goes up as well. And so how does that make sense? Well, if you think about it, if I just need to drag two little tiny plates past one another, I'm not really deforming that much fluid. There's not that much area that shear stress is acting over. Where if I have two big plates and I'm trying to drag these big plates, I need to deform all of that liquid between them, right? And in that case, I need a lot more force to do it, right? So the force scales with the area as well. Now, the final parameter that we haven't really investigated too closely is h. So if h goes up, the force applied goes down. So what's going on there? Well, in the set, you know, what does this mean? If I have these two plates very close together, and I'm moving them, the velocity gradient between those two plates is going to be very big, right? So in this case, for this particular problem, dvx dy was basically the same as v plate divided by h, right? In a sense, you know, this problem, it just kind of worked out nicely that our velocity gradient happened to essentially be delta v divided by delta y. You know, so dvx dy is sort of the same as delta v delta y. So for this problem, you know, the bigger your h, the smaller your velocity gradient. And if you look back to your constitutive relationships for Newtonian fluids, the smaller our velocity gradient, the smaller the shear stress. And of course, the smaller the shear stress, the smaller the force, right? So what does this mean? If we increase h, then we decrease our velocity gradient. If we decrease our velocity gradient, we decrease the shear stress. If we decrease the shear stress, we decrease the required applied force that's needed to move the plate. So there it works out. So what have we done? We've finished now creating a connection between force and the velocity of the plate and also some other known parameters. And we kind of got to force from shear stress. We got to shear stress with velocity gradients. We used velocity gradients to get a velocity profile, and the velocity profile was what allowed us to relate it to things like the velocity of the plate and some other problem parameters. So, oh man, we actually skipped a couple steps. We definitely integrated applied boundary conditions, and we just finished talking about the relationship between shear stress and the forces required to generate it. So, hopefully this has been a helpful and useful and interesting part one of our lecture, where we sort of did practice solving differential equations and also made connections between shear stresses and forces and velocities. Thank you very much, and good luck with your fluid studies.